Today we're going to discuss one of the next major topics that we're going to go to in our study of trig. We had covered the basics of trig as circular functions, the unit circle, and trig graphing, and now we're going to move on to the ideas of trig identities and trig equations. And for this video I'm just going to focus on trig equations. We'll be able to utilize our knowledge of the unit circle to basically come up with some solutions to equations involving trig rather than just algebraic expressions like you might have seen in Algebra 2. So let's say we have an example, something like 2 minus the, or let's say 1/2 minus the sine of x is equal to 0. So our idea here is going to be very simply isolate your trig expression and then use your knowledge of the unit circle to be able to come up with a solution. So if we add sine of x to both sides of our equation, we get the resulting equation that the sine of x is equal to 1/2. Now generally in situations like this you'll be given some guidelines and you might be asked about solving for x as it is on the interval from 0 to 2 pi. You would see a hard bracket on 0, meaning that we're including 0 as our smallest angle, and a soft bracket or a parenthesis on 2 pi, meaning that we're not going to include 2 pi. So basically what they're saying is, in one trip around the circle, find me all the places where the sine of x, the sine of some angle x, equals 1/2. And so now you go into your thought process and say, okay, well I remember that as far as our coordinates go, it's cosine, comma sine, and that cosine goes with x and sine goes with y. And so if we need to come up with a solution where the sine of an angle is positive, we're going to be looking for angles that leave us in the first two quadrants. And then it's a matter of, okay, well, this triangle must have an opposite side of 1 and a hypotenuse of 2, and you should recognize that angle in there being the angle we're solving for as 30 degrees or pi over 6 radians. Since our directions told us that we're looking for angles between 0 and 2 pi, we can assume radians, and so we say, okay, well, our x is pi over 6. But this is where you have to have a full knowledge of the unit circle, because you've got to remember that as you move around to the second quadrant, you're going to find another angle that has that same opposite side of 1 and a hypotenuse of 2. And that angle over there, the reference angle, of course, is still pi over 6, but the angle that got you there would be 5 pi over 6. And you could think of that as this being pi over here, this side, and that being the same as 6/6. So if you were to move around and stop 1/6 short of 6/6, you'd be at 5/6. So we can include that as our other solution, 5 pi over 6. And there we have two solutions for this trig equation, 1/2 minus sine of x equals 0. So that's a very basic intro level trig equation, but it gets you the fundamental idea of what you're looking for. Isolate the or the trig expression, whether it's sine, cosine, or tangent, and then use your knowledge of the unit circle to come up with the solutions. Notice I say solutions because almost always you're going to get about two solutions with these things. Okay, so we're going to move on to a second example here. This one a little bit more complex, but again, kind of the fundamental strategy remains the same. We're going to try to isolate the trig expression, being this cosine here that's being squared. We're going to try to isolate that and then use our knowledge of the unit circle to come up with a solution. So first off, in case you haven't seen this notation before, with the cosine being squared with the exponent being there in front of the x rather than after the x, it's something mathematicians do as a way to use some clarity. For example, the cosine of x, that if you were to take an angle and take its cosine, you would come up with the cosine of x. To say the cosine of x squared would mean find that cosine and then that value, which would be a number between -1 and 1, and then square it. You could see how somebody might get confused if I were to write without the use of the parentheses, in that you might wonder, hey, are we going to take this angle and then square it? You know, take pi over 6 and then square that and get pi squared over 36, and then take the cosine of that angle, or are we going to take the cosine of the angle and then square it? Well, the answer, well, if it's written this way, that would mean we're going to square the angle first, like I just described. However, we're almost never going to do that in this class or in most of our applications. But if we did want to do that, that's the way it would be written, or maybe they would go so far as to put some parentheses in for here for clarity. However, to avoid the ambiguity there and to not have to use parentheses all the time, what mathematicians have done is put that exponent there over the cosine to imply that you're going to take the cosine of the angle first and then square it. So now that we know that, we can say, okay, let's work on isolating our trig expression. So we can use our basic algebra skills and add 1 to both sides, and we're going to get 2 cosine squared of x equals 1. And now again, we still have to isolate our cosine, so we're going to divide both sides by 2, and now we have the cosine of x squared is 1/2. And now, to further isolate it, to get it all the way by itself, we have to remove that squaring. So we're going to come along and take the square root of both sides. But this is a key step, just as you should remember from your algebra. Whenever you take the square root of a positive number, you got to remember it has 2 square roots, a positive root and a negative root. So as I take the square root of the cosine squared on the left side, I'm going to write plus or minus the square root of 1/2 on the right side. So that our left side simplifies to the cosine of x, but our right side is plus or minus the square root of 1/2. Now, you may not recognize that fraction, but that's one of my good friends from the unit circle. If you think about how square roots of fractions work, you could say this is the square root of 1 over the square root of 2, and everybody should know the square root of 1, of course, is just 1. So it's 1 over root 2. You say, well, we have a radical in the denominator, so let's go and quote-unquote fix that. Multiply top and bottom by root 2, and we get root 2 over 2. And that's one that you should certainly recognize as being real familiar from the unit circle, and more importantly from the angles involving pi over 4. So thinking about our cosine being root 2 over 2, cosine of x equals root 2 over 2, whether it's positive or negative. If we recognize that as the pi over 4, which we should, we could think about that angle being, say, here in the first quadrant, and one solution, of course, would be x equals pi over 4. Now, as far as positive cosines go, that's going to be cosines that are on the right side of the circle. So the other place that the cosine would be positive, root 2 over 2, would be down here in the fourth quadrant. So you could think of it as 1 pi over 2, 1 pi over 4, 2 pi over 4, 3 pi over 4 here. 4 pi over 4 would be the same, of course, as 6 pi over 6, which we saw before. 5 pi over 4 down here, 6 pi over 4, which is the same as 3 pi over 2. And then lastly, 7 pi over 4. So our two positive values of root 2 over 2 are going to be pi over 4 and 7 pi over 4. And then, of course, we're going to get our negative solutions over here on the left side at what I mentioned before is 3 pi over 4 and 5 pi over 4. So this is a trig equation that has 4 solutions in one trip around the circle. We'll add 3 pi over 4 and 5 pi over 4 to that. And so there you go. Any one of those angles, we could plug those values in, just like we can in any algebra problem, into our original equation, and it would yield a true statement. But that's something to look for. If you see the square root of 1/2, you should quickly be able to realize that that's root 2 over 2, and then quickly be able to realize that that's going to be your pi over 4s. Whether it's positive or negative, it would just be a matter of which of those pi over 4 angles you're going to be taking. Okay, so we'll look at one more that involves a squared quantity. This time it's a tangent, right? And so we're going to go about our same process. We're going to add 3 to both sides and get tangent squared of x is equal to 3, and then take square roots of both sides just like we did in the last problem. And remember that we're going to do the plus or minus thing on the right side. So that's going to yield the tangent of x is equal to plus or minus root 3. And probably a little less familiar with tangent values from your unit circle than you are with sines and cosines. But if you think of tangent as opposite over adjacent or sine over cosine, as we talked about before, that can certainly help you. So you may want to imagine this as being over 1, if that helps. And you could think, okay, well, if we're thinking about our unit circle, tangents that are positive and negative, we could be in any one of the 4 quadrants. So again, this looks like one where we're going to get 4 solutions. 2 solutions will give us positive tangents, and 2 will give us negatives. 2 of the quadrants, that is. So let's think about what angle would have a tangent of root 3 over 1. So if we remember that it's the 30, 60, 90 that has root 3 as one of its side lengths, you can think of, okay, the 30-degree angle, which is pi over 6, has 1 across from it and root 3 and then a 2. And you think about this as opposite over adjacent. And you think, okay, for the opposite side to be root 3, we're looking at the 60-degree angle, which is our pi over 3. That's the guy that would have the opposite side being root 3 and its adjacent side being 1. So our angles are going to be pi over 3s, or 60 degrees, in every quadrant. So if we think about being in the first quadrant, that of course is just going to be pi over 3. So we can start making a little list of our solutions here. X equals pi over 3. And in the second quadrant, oh, by the way, that's of course a positive tangent value because it would be root 3 over 1. In the second quadrant with a reference angle of pi over 3, and we'd be looking at this triangle where that's pi over 3. That, of course, is root 3. This time it'll be negative 1 as the adjacent side, though, because we're to the left. But the question is, what is this angle that got us there? And if you think of this as 3 pi over 3, being 1 pi, and we're on our way over to 3 pi over 3, but we stop 1 pi over 3 short of that, that means we must have gone 2 pi over 3. So our second angle, that blue one that I just drew in there, would be 2 pi over 3. And that'll be our next solution. And if we keep moving along now to the third quadrant, and we go pi over 3 down from the x-axis, the opposite side would be root 3, the adjacent side would still be negative 1. Of course, the opposite side is negative as well. And we could think of that being having gone to 3 pi over 3 plus 1 more pi over 3. That would be 4 pi over 3. So there's our third solution. And then lastly, we'd be all the way over into the fourth quadrant with a reference angle of pi over 3. The opposite side would be root 3, be negative there because we're going down, but the adjacent side would be 1, so to be a negative tangent, negative root 3 over 1. But that angle is, well, we could think of going all the way around as 6 pi over 3, and having stopped 1 pi over 3 short of that, that would have been 5 pi over 3. So there's our 4 solutions for this problem. And by now you start to get a sense of this stuff. The problems are always going to be rigged so that they come out to be side lengths of our 30, 60, 90s or our 45, 45, 90s, or again, they could always turn out to be quadrantal angles, the ones that are on the axes. Okay, for our last example, we're going to ramp it up a little bit. Now we have what looks very different from the ones we've done before, where we have a squared term, a squared trig term, but we also have a like a non-squared term, almost like quote-unquote like a linear trig term, and a constant. So for this, I need you to be a little bit inventive and kind of understand, maybe back to our regular old algebra skills. I'm going to just put this sine of x in red, sine squared in red there, and this guy in red. And maybe you can sort of think of, temporarily anyway, sine of x just maybe being equal to some like dummy variable like, let's use w. And if I were to rewrite the expression that I had in this first problem, where it said sine squared, and if I'm just going to let sine squared be called w for a second, then I could rewrite that as w squared. So I'm going to have w squared, and then I'm subtracting sine of x, which I've called w, so I could say, okay, I'm going to subtract w, and then I'm subtracting a 2. And if you could temporarily just kind of forget all about this trig, scary looking trig thing up here, and just focus on this nice little equation down here, you should certainly recognize equations like that from Algebra 1, if not Algebra 1, certainly Algebra 2. And you say, okay, well, I've got a quadratic equation. How do I solve these things? And the key is, first go-to technique is usually factoring. So if we could factor this into 2 things, we're saying, all right, let's find 2 numbers that are going to multiply to get -2 that add to get -1. Think about that for a minute or two and think those two numbers would be -2 and +1. So this thing is going to factor to w plus 1 and w minus 2 equals 0. And you should recall from your algebra skills that you can set either one, or you can set really both of those factors equal to 0 to get your solutions. So w plus 1 equals 0, or w minus 2 equals 0. So you get two different options there. First one, of course, gives us w equals -1, and the second one gives us w equals 2. And you say, okay, well, there's our solutions. Except the original problem, didn't say anything about w's. We introduced w as the sine of x, so what we want to do now is kind of like back substitute. We made a little substitution here. We took sine x out and replaced it with w. Now we're going to have to pay for that. We're going to go and take the w out and put a sine of x back in. So we're saying that the sine of x, the sine of x is equal to -1, or the sine of x equals 2. Now, we're going to treat these two cases kind of independently. We think, okay, here's our unit circle idea, the coordinate plane, and the sine equaling -1. As you remember, we've got the 4 key spots as you move around the circle: 1, 0, 0, 1, -1, 0, and 0, -1. And if you remember that sine is the y coordinate, the only place the sine is equal to -1 is down here. And so that angle in one trip around the circle between 0 and 2 pi is going to be right there, and that angle is 3 pi over 2. And that's the only solution for that. In that, we're not like the previous examples, we got at least 2, sometimes 4 solutions with these trig equations. This one's only going to get 1. So we can call that a victory, but then we come over to our other factor here, the one that gave us w equals 2, or sine of x equals 2, and we say, okay, well, let's just think about where the sine's equal to 2. And you can think real hard, but there are no solutions to this because there's no place where the sine of an angle would be 2. If you think of it as 2 over 1, to have an angle have a sine of 2, that means the opposite side would have to be 2 and the hypotenuse would be 1. And you should know full well that the hypotenuse has to be the longest side in a triangle because it's across the biggest angle. So what we get there is basically just kind of think of it as an extraneous factor that doesn't give us any solutions to this problem. And our only solution for this whole equation is x equals 3 pi over 2. And that'll happen often in these problems that have quadratic patterns in them. You might get one factor that yields a solution or two, and the other factor yields none. Sometimes both factors will give you solutions. But there you go. There's a nice little entry into the world of trig equations and solving them.